Okay, today we are proving divergence theorem. This is, well, that I named it Fundamental Theorem of Calculus 5.0. This is the last one. And this is one of the biggie out there. People use this all the time. When you take, wait, are you planning to take ENN in physics? If you do, and then Gauss's law is divergence theorem. Okay, this is a big deal. So let's just take a look at the statement itself and then try to understand what it's trying to say before we prove it. So divergence of the vector, let's just look at this side first, okay? We have talked about curl versus divergence of vector field, and vector field has three components, I component, J component, K component. So this I component has something that is only moving in X direction, positive or negative X direction field. And this one is positive, negative Y direction, and this is vertical, positive or negative Z direction. Good? So when we have a diverging field everywhere inside this volume, then this whole thing is expanding. Remember the divergence, right? If you dot del with this thingy, then if we have enclosed region like this is our surface, then it has to leak through the surface. You know what I'm saying? If it's expanding field, it has to come through, so it will penetrate the surface. If you have a curl, only some kind of swirling, like tornado looking without expanding thingy inside, then nothing, it's possible to have nothing coming through this surface. You know what I'm saying? But just because it's a diverging field, so we have to have some kind of flux count, they call it, right? Coming out is, we count that as positive in a dot product, and going in, conversely, if you have negative divergence, then something is going in, and meaning there's some kind of sink that absorbs the field. And then we have to have a negative total flux count, right? So whatever's diverging everywhere in this surface, then it has to come through the surface of this thingy, the region. You know what I'm saying? So this is the boundary. The surface is the boundary, and internal volume, they call it E. So I'm calling that internal part E. And this is surface boundary, S. Okay, of the region. So whatever is diverging out of those region E, if you add them up, they have to all come through the surface, the boundary. So we are still relating the interior versus the boundary. Good. Let's look at this side. So F dot ds, this is our surface integral that we've been practicing, right? So something is coming through the surface and we are calculating all of that. But there is this dot product, okay? Any question about what this is saying, and do you wonder why there's a dot product? Let me get into the preliminary part of that before we do the proof. Say there are surface field going this way, right? And then say there is a perpendicular area, surface is catching those flux count, okay? But compare that to another, say that thing, okay? This area is a lot bigger than that area, but as you can see from the picture, it'll catch exactly same amount of flux lines, right? The field lines. Good. So whatever this thing is catching, the blue surface is catching has to be exactly same as the red surface is catching. You know what I'm saying? Let's call this area ds, our usual ds, tiny infinitesimal ones that has been blown up. Okay, then we cannot just multiply the field. When we say field, it kind of means field density. So we cannot say F times ds, right? It has to be really this perpendicular. Whatever is perpendicular to the field is the one that counts, right? So we need to figure out what the area of this thingy is. If this thingy is ds, and let's call that angle theta. then it has to be the field density F and ds. And this area of this thing, do you see this is ds times cosine theta? Hey? Right triangle right there. Because it has the same amount of width. And this side is that side times cosine theta now, isn't it? So the total flux count here is F times ds times cosine theta, isn't it? Wait a minute, that looks like a dot product now, doesn't it? So this is same as F dot our ds, which that MIT professor called NDS, normal vector NDS, but our book just calls it vector ds. You get it? That's why there is ds on this side. I mean the dot product on this side. You get it? And this is just adding all of the divergence of the field over this. So this, there's a parenthesis, if you will, right there. Y'all understand what's going on? Okay, I'm not sure if you were able to stay awake yesterday, but MIT still uses chalkboard. Last time I checked, even to this day, they have the electronic ones that moves up and down by the switch, but it's still the chalkboard. Amazing, huh? Okay. Now, so if I take this thing apart, the vector field F has PQR in it, right? All function of X, Y, and Z, 3 variable function. And then we are dotting that with ds, so this field is potentially coming out in every direction, and then we are dotting it is entire surface. Good, that's on this side. The other side, divergence is just a dot product of this thing with a del. So you have partial P, partial Q with respect to Y, and partial R with respect to Z, and you add them up. That's what divergence is, right? Now, I'm just matching the P part, X part with this X, and then Q part with this Q part, and R part with that R part. So I've broken this up into 3 different subintegrals. Now, you may say, just because this is true, does that automatically mean these 3 are true? Well, they don't have to be. It could be, but we don't care. We don't need that. The way I'm going to prove is if I can prove these 3 individually, then we can add integrals, correct? So we add the integrals, then we can prove this. So this symbol only needs to work that way. And converse does not need to be true. So we don't care if the converse is true or not. Do you understand the plan so far? That's what he did without really explaining a whole lot in detail about it. Good, but do you agree that if all 3 of these can be proven and are true, then that makes that entire statement, this big statement, true? Good. And then only thing he did was this third part, which is what I'm gonna do. The other 2 are about the same thing, okay? So far so good. So I'm going to prove this case only the vertical field, either moving upward or downward with a Z part, okay? And the other 2 you have to, now then the next thing is that he worked on this region, right? It's vertically simple region, and if it's not vertically simple, you slice it to make it vertically simple. You want me to redraw that bagel that he drew, or are we good? Do you even remember what bagel I'm talking about? See, this thing is vertically simple, meaning we have a top surface, bottom surface, and side is lateral. You know what I'm saying? Some vertical side. But if we don't have that, and this was the picture, if we have this kind of surface, now what are you gonna do? And then this is what the professor did. You slice it to a bunch of vertically simple regions. You know what I'm saying? So you have this thingy, this thingy, this thingy, this thingy, 4 different things. Then you can apply whatever we are about to prove here. There's a top and the bottom, top and the bottom. And then integrals do add, so we can just put it together. So what we are proving is really only 1/6 of entire proof. You know what I'm saying? Pretty simple region, and that's just case 3. So far with me? Okay, any question before I start proving it? I'm gonna copy this thing so I can recycle it down here. Okay, so here we go. This is proof of 3. Okay, and the other two are very similar, so this will convince you. Okay, now I'm going to split these things into S1, which is a top surface, and S2, which is a lateral surface, and S3, which is the bottom surface. So far so good? Now the top one, this one, I'm going to call this surface C is equal to 2 variables. He called it Z1, but let's just call it F of X and Y. And this bottom surface, this one we are going to call this G. Z is equal to G of X and Y. How's that? Good. And then I'm going with our book's notation. So this interior of this region is called E. And then S is, of course, the boundary. And this region, we are going to call it D, which he called U yesterday. Are you with me with the setup? Now let's take a look at the right-hand side, this part, right? I'm going to evaluate that and compare. I'm going to evaluate this and compare if they are the same thing. That'll complete the proof. Okay, so let's write down the right-hand side, triple integral of E, and then partial R, partial with respect to Z, and then we have dz, and then dy, and dx is our triple integral, correct? Right here. Okay, now let's see. This thing, of course, is double integral and of that region D, and then we can integrate this part, because remember this is a derivative, antiderivative relationship now, isn't it? So we find the antiderivative, which is of course R, and that R has variable X, Y, and Z. Say yes. I jumped. I'm gonna. Okay. I'm gonna do this. I'm gonna take extra step so that you clearly understand what's going on. This is D, and this part is partial R with respect to partial Z and dz, and the lower limit is when Z is equal to G of X and Y, and upper limit is F of X and Y, correct? That's how we evaluate the integral, and the rest is just dy over dx. Good? So I'm evaluating this inside integral like that. Good? So we are supposed to plug in G of X and Y and F of X and Y for our Z value, correct? And then we will have the dy and dx. With me? Now we plug it in. So we have region D. This goes into Z because we just integrated with respect to Z. Good? So we'll have R of X, Y, and instead of Z, we plug in F, X, Y. Good? Minus, and then we all have R and still X and Y, and then we plug in G of X and Y. dy dx. You with me? So we have got to double integral over this region so far. Good. Okay. Now we're going to work on the other side. Okay. The other side is this. Our double integral, where double integral of our surface S enclosed, and then we have f dot dsa right here. Well, not f dot ds, I forgot. I'm only doing this part, r dot ds. Okay, so change that to r, function of x and y, x, y, and z, and then with a make it a vector, then dot that with ds is what we are doing. So far so good? Say yes. Okay, now let's do the top part first, shall we? Okay, the top part. Say we have this S1. Okay. Now the top part is then we'll calculate ds. Do you remember how we used to calculate ds? Or should I run that by you again? If you want to see it now is a really good time.
Can you show it again?
Yeah, okay. Let's review how we did this. So we have some kind of vector function R with x and y, right? And we can parameterize it like this, x, y, and then this part is, of course, our f of x, y, k vector, like that, eh? Hopefully you remember this thingy. Then we take a partial derivative with respect to one variable. So this becomes I vector plus 0 j vector plus partial f partial x k vector. You with me? Okay. And then you take another partial derivative with respect to other variable y. Then this will be 0 I vector plus 1 j vector plus partial f and partial y k vector. Good? Say yes. Okay, now our ds is the cross product of these two, isn't it? dr dx cross dr dy dx. You know what I'm saying? Okay, so let's take a cross product. I'm going to move this thing over here, about that much. And we can imagine letter I, j, k there and do it. So for I vector, this is for I vector right here, we have this thingy minus this thingy. Good? So negative partial f partial x. You with me? Okay, for j, and j is already a negative, right? Minor. And j is this minus this. So you have partial f, partial y. Good. And plus k. And with a k, cross this out, so it's this minus this. So we just have 1, k. Good. And then, not to forget, dy over dy times dx. That's our ds. So far, so good. Now we are going to dot it. So our integral looks like this, s1, and then r, function of x, y, and z. But this one only has k component, correct? Of ds. So these two die, right? We only have this one. Are we good? Okay, so what we have is double integral of r dy dx. Okay, but let's just think about this thing. What is the argument? What are the variables inside of r? Okay, let's just take a look at this thing a little bit. This thing has originally x, y, and z in it, right? Now we have a problem because we don't have z. What is our z? We are supposed to plug in these things. Remember that when we do a surface integral? This is x, y, z. I used to write it like this. This is x, this is y, and this is z. You know what I'm saying? So we have to make that substitution when we do this, correct? So instead of x, y, and z, what I have to do is put here f of x and y. And this is over S1. Are you with me? Are you with me? Okay. Now let's do S2. S2 is this lateral area. Okay. Now, let's just think about this logically. If you have some kind of normal vector, let's say, sticking out perpendicular to that surface, and this is our ds. Good. And then our field is only vertical now, isn't it? So our field is on either pointing upward or downward. That is our r of k vector. The keyword here is k vector. Good. So yes. Then what is the dot product of the two? What is r k vector dot with our ds vector? That has to be 0, right? Because dot product, when it's 90 degrees, gives you 0. And that is the motivation for this setup, just the vertical field only. And we break this field down into 3 different components and do it separately. You know what I'm saying? You with me? Okay. Of course, if you wanted to prove it for the horizontal component, let's say the j vector thingy, then we are not going to cut up this. I mean, we are not going to use the surface. If we are using this very surface, then I have to split it so do this half and that half. Okay. Anyway, so S2 is easy, it's done. Okay, let's do S3. S3 is the bottom. This looking thingy, right? Okay. So this function, remember, was c was g of x and y. Good. Okay. You want me to set up ds one more time? Nay? Do you get the feeling that this ds will be opposite direction? So partial g, partial x, I vector plus partial g, partial y, j vector. That's ugly j. And then minus k vector. Do you believe it? we have to set it up in a way. We have to take a cross product, so in a way it actually points downward now, don't we? Because conventionally the outward normal vector is outside. You get it? So we have to switch the order of the cross product to make sure that this is opposite direction of our top surface. So far, so good. Now we're going to take a dot product. So double integral over S3 of R K vector and dot ds vector turns out to be, and these two die once again, right? And then it gives you negative sign of the double integral of S, not S3 anymore, D. Did I put S3 on top? Ooh, D. Our region D, right? This D. Because once you take a dot product and then do this, then it's a double integral over this region, D. Good. I screwed that up earlier. Okay, of our R. Now we have X, Y, and once again, we are substituting these things, right? So here is our G, just like what I did here, F. You with me? Who's confused? So that surface only exists and G of X and Y. And then dy over d. Good? Say yes. Okay, now we'll add them up. So our integral, therefore, our entire S of your R K vector dot ds, all of it, is the integral over S1 plus integral of this thing over S2 and integral over S3, isn't it? Are you good? Okay, now we just write down the result that we have. So here, what we had was this thingy. This thingy is what we got. So we have integral of the region D. D, why can't I write D? D, R, K dot, no, just R, K, and X, Y, F of X and Y, dy dx. Good. I'm just copying this thingy down, that thingy right there. And this one is right above here. Why don't I just copy and paste it? That's a more convenient way of doing this. That thingy. Okay, and all we have to do is compare this with whatever we had up there at the end. Ah, that's exactly the same thing, isn't it? This integral minus that integral over D. How about that? You get it? So therefore, we can conclude our triple integral over the region E of partial R of partial Z, and then dz, dy, dx is equal to exactly same thing as double, oh, forgot that circle thingy there, double integral over S of R K dot ds. And this is the part 3 of this statement. Good. Say yes. Let's recap. So what we have proven is this part. This part on a vertically simple region. Now we put different regions together, which is in case it's not vertically simple like that. So we can expand this dot into all weird looking region. And this is just still part 3. Good. And now similarly, you can prove part 1 and part 2 for all regions. And then we add these things vertically, and then that gives us this statement, which is exactly what divergence theorem is saying. Oof. No wonder you didn't get any of this yesterday, huh? You kind of went through this pretty fast, all over the place. Any questions?
Yeah, can you scroll down to like the final statement?
It's not really final statement. It's this only into the Z component of the field. Oh, this looks weird. This is E. That's E. So now you know how to prove divergence theorem.